Massive stones still stand where ancient builders placed them thousands of years ago. This video uncovers the hidden engineering principles behind Bronze Age construction, the forgotten rules that allowed our ancestors to achieve the impossible. You will learn exactly how societies without modern technology erected monuments that challenge our understanding of history itself. How did they move stones heavier than elephants? And what secret knowledge allowed them to align structures with the stars so perfectly? What does it truly mean to build something meant to last forever? Stone circles and towering mounds began to appear across the land, not as isolated works, but as signs of a profound shift in human consciousness. This was the dawn of monumental ambition. For the first time, communities were not just building shelters for the living. They were creating eternal markers on the landscape, symbols of identity and belief meant to endure for countless generations. This shift from practical construction to symbolic architecture required something entirely new, a societal engine capable of turning vision into reality. It started with stability. The slow accumulation of surplus food allowed for specialization. No longer did every member of a community need to farm or hunt for daily survival. This surplus created the world's first professional class of engineers, architects, and master craft workers, individuals who could dedicate their lives to solving complex problems of design and logistics. At the same time, clearer social structures emerged, providing the necessary leadership and organization to marshal these specialized skills. A single visionary idea needed a coordinated effort to become a mountain of stone. Think of the immense trust this required. People had to believe in a project they would never see finished, investing their labor in a legacy for their descendants. What powerful belief or shared purpose could compel such a long-term commitment? The answer lies in the very structures they left behind, silent testimonies to the first time humanity dared to build for eternity. The choice of stone was the first critical decision, a testament to an engineering wisdom written not in books but in the landscape itself. These builders were master geologists, reading the Earth's bones with an intuition born from deep, generational observation. They learned to identify the perfect rock not just for its strength, but for its hidden qualities, its workability, and its resistance to the relentless pressure of time. They sought stones that could be shaped yet would never yield. Limestone, for instance, could be precisely worked with simpler tools, making it ideal for intricate carvings or tightly fitted joints. Granite, on the other hand, was chosen for its immense crushing strength, perfect for the foundational stones that would bear unimaginable weight. This was not a random selection. It was a science. At quarries, we see evidence of their systematic approach. They learned to follow the natural grain of the rock, identifying hidden fracture lines. By driving wooden wedges into these cracks and soaking them with water, they could harness the swelling force of the wood to split colossal blocks from the bedrock with astonishing precision, a technique that turned a mountain into manageable building blocks. Consider the great trilithons at Stonehenge, those iconic doorways of stone. Each massive horizontal lintel was not simply dropped onto its uprights. The connecting surfaces were subtly shaped, often with tongue and groove joints carved directly into the rock, locking the structure together. This shows a profound understanding of how these specific stones would interact under stress, creating a unified, stable form. How could such precise material science emerge without laboratories or testing machines? The answer lies in a lifelong conversation with the environment, a process of continuous experimentation where failure was as instructive as success. Every cracked stone taught a lesson, every successful structure confirmed a hypothesis. slowly building a body of knowledge that would be passed down through the voices of countless craft workers. This intimate relationship with rock was only the beginning, for knowing which stone to use was meaningless without knowing how to move it. But moving the stone was only half the battle. The true challenge began when it reached the site where a different kind of genius took over, the mastery of cosmic geometry. With nothing more than wooden stakes and lengths of rope, ancient surveyors plotted perfect circles and precise alignments across vast distances. Their canvas was the earth itself, and their blueprint was the sky. They were not merely stacking rocks, they were weaving the movements of the sun and moon into the very fabric of their monuments. At Newgrange in Ireland, for example, a narrow passage leads deep into a massive mound. For just a few precious minutes at dawn around the winter solstice, a blade of sunlight pierces through a special opening above the entrance, flooding the inner chamber with light. This was not a lucky accident. This was deliberate, sophisticated engineering that required an intimate understanding of the solar cycle, a feat of alignment planned and executed with stunning accuracy. How could they achieve such precision with such basic tools? The secret lies in the elegant application of simple geometry. By creating large circles from a central point with a long rope, they could establish perfect boundaries. By creating right-angled triangles with ropes knotted at specific intervals, they could lay out square foundations. These were not just abstract shapes, they were the key to stability. Symmetrical structures distribute weight evenly, preventing weak points that could lead to collapse over centuries. Perhaps the most fascinating clue is the evidence of a shared measurement system. Researchers analyzing monuments across Europe have found that many were built using the same standard unit of length, a prehistoric yardstick. This suggests that knowledge was not isolated, but traveled along ancient trade routes, a network of shared engineering principles connecting distant cultures. This shared language of measurement allowed for the replication of successful designs, proving that these builders were part of a wider community of thinkers. They were applying a universal set of rules, turning chaotic landscapes into ordered, eternal statements. The perfect orientation of a stone circle to the midsummer sunrise is a testament to this deep connection between earthly construction and cosmic observation. It reveals a society that saw itself as part of a larger, orderly universe and built its most sacred spaces to reflect that harmony. Yet, even with perfect alignment, a structure is only as strong as its foundation. So how did they ensure these colossal weights would not simply sink into the earth? The ground itself became a tool in the hands of these ancient engineers. Moving a stone heavier than a modern bus required more than brute force. It demanded a deep, intuitive understanding of physics. Picture a massive sledge, a wooden platform carrying a monolithic block, resting not on solid ground but on a track of carefully laid logs. As the sledge was pulled forward by teams of workers, rollers at the back were constantly picked up and moved to the front, creating a continuous, rolling path. This simple system transformed sliding friction into the far lesser rolling friction, a fundamental breakthrough that made the impossible seem manageable. But the true innovation came in the details. Experiments have shown that wetting the path ahead of the sledge, or using a slurry of mud and water, could reduce the pulling force required by half. These builders were not just using simple machines, they were actively engineering the interface between their load and the earth, manipulating friction itself to achieve miracles of logistics. Coordinating such an effort required a social machine as sophisticated as any physical tool. Evidence from sites across the ancient world points to highly organized labor forces, not chaotic mobs. There were specialists for every task, from the workers who positioned the rollers to the teams hauling on the ropes, all moving in a synchronized rhythm guided by calls or drumbeats. This was prehistoric project management on a grand scale. At some monuments, archaeologists have found remnants of worker settlements that suggest a shift system was in place, with teams rotating to maintain constant progress without exhausting any single group. Feeding, housing, and motivating a large workforce for projects that spanned generations required a level of administration we are only beginning to appreciate. How did they manage this without written records or instant communication? The answer lies in a powerful, shared culture and oral tradition. Complex information about routes, techniques, and safety could be encoded in stories, songs, and rituals, passed down and refined with each new generation that contributed to the work. The journey from quarry to construction site was a carefully planned operation. Builders did not simply take the most direct route, they chose paths that played to their strengths, often following riverbanks or coastlines where possible. For water transport, they devised immense, buoyant rafts to carry stones that would sink a conventional boat. Some of the largest stones were likely floated on the tide, moved at just the right moment to harness the natural power of the rising water, a testament to their ability to work with the environment rather than fight against it. Over land, the routes were meticulously prepared, with obstacles cleared and the ground leveled to create a stable causeway for the heavy load. This entire process, from the quarry to the final placement, was a single, seamless logistical chain. It connected the raw material of the earth to the vision in the sky, a tangible flow of human effort and intelligence. The movement of the stone was a ceremony in itself, a physical manifestation of a community's collective will, proving that the true monument was not just the standing stone, but the incredible journey it took to get there. The sheer physics of lifting these stones seems to defy human capability, but ancient builders discovered a secret conversation with gravity itself. They learned that a long, sturdy timber could become a powerful ally. By placing a pivot point or fulcrum close to a massive stone and applying pressure to the far end of the lever, a small team could generate enough force to lift a weight that would be utterly immovable by hand alone. This principle of mechanical advantage transformed their efforts, turning impossible tasks into systematic, manageable steps. It was a silent agreement with the laws of nature, a way to make the world itself help them build. Archaeological evidence reveals even more sophisticated systems. At sites where massive stones were raised, we find traces of earthen ramps, built up gradually to allow workers to drag loads to ever greater heights. But the true ingenuity lies in the use of cribbing, a technique of stacking timber into a box-like structure that could be incrementally raised, creating a stable, adjustable platform to support a stone as it was inched upward. Think of it as a prehistoric hydraulic jack built from wood and human intelligence. Some researchers suggest they may have even used a primitive but effective crane, the shadoof, a counterweighted lever commonly used for lifting water, but scaled up to handle blocks of stone. The ultimate test of this knowledge is found in the Corbeled arch, a masterpiece of prehistoric engineering. To create a roof or a passageway, builders would stack stones in successively higher layers, with each new layer projecting slightly inward over the one below. This creates a soaring, vaulted space without a single supporting beam. The genius of this design is in the distribution of weight. The force of the stones above is channeled down through the overlapping layers, transferring the load to the thick walls on either side. It is a self-supporting system, a testament to a profound understanding of how to guide immense pressure along a desired path. Experimental archaeology has proven these methods are not just theoretical. Modern teams, using only the tools and materials available in the Bronze Age, have successfully quarried, moved, and raised multi-ton stones. These experiments reveal the subtle, accumulated knowledge embedded in these techniques. The exact placement of the fulcrum, the type of wood used for levers, the ideal angle for a ramp, all of these details were refined over generations. Each successful lift added to a growing body of practical physics, a tradition of problem-solving passed from master to apprentice. What everyday observations sparked such revolutionary ideas? Perhaps it was watching a child on a seesaw or a large branch used to dislodge a boulder. Maybe it was the simple act of prying up a heavy object with a strong stick and noticing how the right pivot point made the work effortless. These moments of recognition were the seeds of engineering. They saw the hidden potential in a fallen tree, understanding that the natural world was full of invisible levers just waiting to be used. This ability to see solutions in their surroundings, to turn observation into application, was their greatest tool. It allowed them to build not just with their muscles, but with their minds, creating a legacy of stone that still stands as a monument to human ingenuity. The true strength of a monument lies in what you cannot see, buried deep beneath the ground. Before the first stone was ever set upright, Bronze Age engineers were already at work on the most critical phase of construction, the foundation. They knew that a structure meant to last for millennia needed a base that was just as enduring. This required a deep understanding of the earth itself. Teams would excavate down through unstable topsoil, sometimes digging trenches several feet deep until they reached a solid layer of gravel or even the unyielding surface of bedrock. In areas where the natural ground was too soft, they did not simply give up, they built it up. They created artificial platforms using alternating layers of crushed stone, clay, and sand, compacting each layer with immense care. This was not just digging, it was a deliberate process of creating a stable, unshakable cradle for the weight above. How could they possibly test soil conditions without modern drills or core samples? The answer is found in a lifetime of accumulated wisdom. They learned to read the land by observing how water pooled after a rain, by studying the types of plants that grew in certain soils, and by using simple probe poles to feel for resistance underground. Each test pit dug was a lesson in the hidden character of the ground. The discovery of layered foundations at sites across Europe reveals a systematic, almost scientific approach. It was not enough to have a solid base, it had to be a smart one. They understood that water was the greatest enemy of stability, capable of washing away soil and causing catastrophic settling over centuries. To combat this, they engineered clever drainage systems. At the base of some great mounds and stone circles, archaeologists have found channels lined with stone or packed gravel, designed to catch rainwater and guide it safely away from the foundational stones. This was forward thinking on a scale we can scarcely comprehend, planning not for decades but for thousands of years. They were not just building for their own time, they were building for a future they would never see, ensuring that their message in stone would remain standing long after their names were forgotten. This invisible, underground work demonstrates a profound respect for the forces of nature and a brilliant understanding of how to outsmart time itself. The final stone was never truly set in place because the entire structure was designed to breathe. Without a single drop of mortar to bind them, these stones relied on a far more resilient principle, the art of the perfect fit. Builders became masters of three-dimensional puzzles, shaping each block so that its neighbors locked it into position. This was not a rigid, brittle construction. It was a unified entity, a wall that could sway and settle as one. The genius of dry stone construction lies in this flexibility. Each stone was not just a weight, it was a key. Its top and bottom surfaces were painstakingly dressed to create broad, stable contact points, while its sides were often subtly angled or notched to interlock with the stones beside it. This created a network of mutual support, where the friction between stones and the downward force of their collective weight generated immense stability. What knowledge of physics informed such a complex system? It was an intuitive grasp of vectors and force distribution. They understood that by angling stones inward, they could channel the tremendous downward force into a horizontal component that compressed the entire wall together, making it stronger under load. The famous Cyclopean walls of Mycenae stand as a powerful testament to this principle. Their massive, irregular limestone boulders, some weighing many tons, were fitted together with such precision that a knife blade cannot be inserted between them. From a distance, the wall seems like a chaotic jumble, but up close, the careful selection and placement of each unique stone reveals a deep intelligence. Every convex surface found a concave home. Every protruding angle was matched with a receiving space. This was not haphazard work. It was a sophisticated language of form and counterform spoken in stone. This method created structures uniquely suited to withstand the tests of time and earth. In regions prone to earthquakes or seasonal ground movement, a rigid mortar-bound wall would crack and crumble. But a dry stone wall moves with the land. During a tremor, the stones in a Cyclopean wall can shift and adjust minutely, absorbing and dissipating the energy, then settling back into a stable configuration. The wall lives with the landscape rather than fighting against it. This resilience points to generations of observation and refinement. Early builders would have seen how simpler walls failed, learning which shapes created weakness and which patterns brought strength. This accumulated wisdom, passed from craft worker to craft worker, evolved into a reliable system of engineering. It was a collaboration with gravity itself, a way of building that acknowledged the world is never truly still, and that the greatest endurance comes from the ability to adapt. Water was the silent partner in every great Bronze Age construction, a force to be channeled and respected. Beyond simply moving stones, ancient engineers demonstrated a masterful understanding of hydraulics, designing intricate systems to control the flow of water around and through their monuments. This was not a mere afterthought, it was a foundational principle of preservation. The relentless drip of rainwater and the slow creep of groundwater were seen as existential threats to structures built for eternity. To counter them, builders became hydrological experts, reading the landscape to predict water's path and then engineering solutions to redirect it. At the heart of many sites, we find carefully constructed drainage channels, lined with stone or packed gravel, running beneath foundations and along walls. These were not simple ditches, but calculated arteries designed to capture water and guide it safely away, preventing the erosion that could undermine even the most massive stone. How did they grasp the concepts of slope and flow direction with such precision? Their tools were observation and experimentation. They watched how water behaved during a storm, noting which paths it naturally took, and then they sculpted the earth to assist that flow, creating gentle, consistent gradients that ensured water would move where they wanted it to go. This knowledge reached its zenith in places like Knossos on Crete, where archaeologists have uncovered advanced plumbing systems that feel almost modern. Here, terracotta pipes were carefully interlocked and sealed, channeling fresh water into the palace and wastewater out, a testament to a society that saw the management of water as a cornerstone of civilized life. But their hydraulic genius extended beyond preservation to propulsion. There is compelling evidence that some cultures constructed canal systems specifically for moving construction materials. Imagine a multi-ton stone loaded onto a buoyant raft, being gently towed along a man-made waterway, its journey made effortless by the very element that once seemed an obstacle. This was the ultimate collaboration with nature, turning a challenge into the most efficient transport network available. the understanding required for this is profound. It means they comprehended buoyancy, they calculated the volume of water needed to float immense weights, and they manipulated water pressure to ensure their canals remained full and functional. This was applied physics on a grand scale. Every drainage channel and every transport canal stands as a monument to a different kind of intelligence, one that looked at a flowing river or a rain-soaked hill and saw not a barrier but a tool waiting to be mastered. The stones themselves seem to hold a secret language, one spoken not in shape but in sound. Beyond their immense weight and perfect alignment, these monuments were engineered to manipulate the very air around them, creating auditory experiences that were as deliberate as their visual impact. Recent acoustic studies have revealed something extraordinary, that many passage tombs and stone circles function as sophisticated sound chambers. Their construction was not merely about defying gravity, it was about shaping resonance. The dimensions of an inner chamber, the specific curvature of a wall, even the type of stone selected, all conspire to amplify certain frequencies and dampen others. In some sites, a single voice speaking at a normal volume can be heard with perfect clarity dozens of feet away, while in others, a rhythmic drumbeat creates a pervasive, immersive vibration that seems to come from everywhere at once. This was not an accidental byproduct of architecture, it was a core design feature. How did builders without oscilloscopes or digital models achieve such precise acoustic control? The answer lies in generations of careful listening and incremental refinement. They learned through experience that a taller, narrower chamber focused sound waves into a beam, carrying whispers across long distances. They discovered that a corbelled roof with its overlapping stone layers could diffuse sound in a way that made it feel omnipresent, filling the entire space. This was an intuitive form of physics, where the success of a design was measured by the emotional and spiritual impact of the sound it produced. The cultural drive behind this is profound. In societies where oral tradition was the living library of knowledge and myth, the power of the human voice was paramount. A ceremonial space that could amplify a storyteller's words or make a chant resonate deep within one's chest would transform a ritual into an unforgettable, visceral experience. It connected the community not just through shared sight, but through a shared vibration, a collective feeling that bound them to the moment and to each other. This acoustic awareness reveals a holistic vision of engineering, one where the structure, the cosmos, and the human senses were all threads in the same magnificent tapestry. The monument was not just something to be seen, it was something to be felt and heard, an instrument of stone waiting for its human players. These structures were not just monuments to the past, they were perfectly tuned instruments for the present, engineered to create a stable and comfortable environment regardless of the weather outside. Bronze Age builders possessed a masterful understanding of thermal regulation, designing their spaces to work in harmony with the sun and the seasons. This was environmental engineering long before the term existed. They oriented their buildings with astonishing precision, aligning entrances and openings to capture the low, warming rays of the winter sun, while using massive stone slabs or strategic overhangs to block the high, harsh glare of summer. This passive solar principle transformed a building from a static object into a dynamic system that responded to the Earth's journey around the sun. How could they develop such a sophisticated grasp of thermal dynamics without modern instruments? Their laboratory was the world itself, and their data was collected over generations of watching how light and shadow moved across the landscape. The very materials they chose were part of this brilliant system. The immense stone blocks used in their construction did more than just support weight. They acted as a thermal mass, absorbing heat during the day and slowly releasing it through the cool night. This natural process evened out the dramatic temperature swings between day and night, creating a remarkably stable internal climate. In the winter, a sun-warmed stone wall could radiate gentle heat for hours after sunset, while in the summer, the same cool mass would draw excess warmth from the air. The thickness and composition of walls were not arbitrary, they were carefully calculated. Builders selected specific types of stone for their insulating properties, knowing that a dense granite would store heat differently than a more porous limestone. At some sites, we find evidence of sophisticated ventilation systems, cleverly placed air channels that harnessed prevailing winds to create a natural breeze, drawing fresh air in and pushing stale, warm air out. This was not just about comfort, it was about preservation, ensuring that stored food supplies and living spaces remained viable year-round. This deep knowledge of environmental adaptation reveals a society that saw itself as part of a larger ecological system. They were not conquerors of nature, but astute collaborators, learning its rhythms and building their legacy in a way that respected the power of the sun, the wind, and the turning of the seasons. This seamless integration of architecture and environment stands as a quiet testament to a wisdom that understood the true meaning of sustainable design. A shared language of measurement connected cultures across vast and seemingly impassable distances. While separated by mountain ranges and seas, diverse Bronze Age societies appear to have built their greatest monuments using the same fundamental ruler. Archaeologists analyzing sites from the British Isles to the Mediterranean have repeatedly identified a standard unit of length, a prehistoric yardstick often called the megalithic yard. This was not a vague approximation, but a remarkably consistent measure used to lay out the diameters of stone circles and the dimensions of grand tombs. The presence of this shared standard implies something revolutionary, a network of exchanged ideas where architectural blueprints and engineering principles traveled along ancient trade routes. This was a continent-wide web of knowledge long before the first written word. How could such precision be maintained across thousands of miles without a central authority? The answer lies in the creation of master standards, physical rods of wood or stone crafted and preserved by a class of elite surveyors. These individuals would have been the guardians of this precision, traveling between communities and ensuring that a unit of measure in one land was identical to that in another, 1,000 miles away. This consistency was the key to replicating successful designs, proving that these builders were applying a universal set of rules to achieve predictable, stable results. This shared measurement system gave rise to a deeper principle, the power of proportional design. Builders discovered that certain mathematical ratios, repeated throughout the natural world, also produced structures of exceptional strength and beauty. They observed these ratios in the spiral of a seashell, the branching of a tree, and the proportions of the human body, and they encoded these same harmonious relationships into their architecture. The so-called golden ratio, a specific proportional relationship where the whole is to the larger part as the larger part is to the smaller, appears in the layout of numerous monuments. This was not a random aesthetic choice, it was a profound engineering insight. Structures built with these intrinsic proportions naturally distribute stress and weight more efficiently, avoiding the weak points that lead to collapse. A facade or a floor plan following these natural ratios feels inherently balanced and stable to the human eye because it reflects the very patterns we are surrounded by in nature. This allowed for the confident scaling of designs, whether for a small shrine or a massive temple complex. The same set of proportional rules could be applied to create a structure that was both colossal and coherent, its every part relating harmoniously to the whole. The Great Pyramid of Giza stands as the ultimate testament to this principle, its dimensions reflecting a mathematical understanding that still inspires awe. What cultural connections enabled this widespread sharing of knowledge? It was likely a combination of trade, migration, and perhaps even pilgrimage. Master builders, armed with their measuring rods and their geometric secrets, would have been highly valued, their services sought after by chieftains and kings aspiring to create their own eternal monuments. In this way, a design perfected in one river valley could find new life on a distant coast, each new construction strengthening a shared legacy of human ingenuity that transcended any single culture or border. Behind every stone laid by 1,000 hands was a society organized with the precision of a modern corporation. These were not chaotic gatherings of laborers, but carefully orchestrated human enterprises, a form of social engineering as brilliant as any stone arch. The evidence lies not just in the monuments, but in the worker settlements discovered nearby. These were not temporary camps, but planned communities with organized housing, storage pits for grain, and areas for tool maintenance. This reveals a society capable of long-term planning on a staggering scale, one that could house, feed, and manage a workforce for years, even decades. Specialization was the engine of this efficiency. Just as in a complex machine, every person had a specific, vital role. There were the quarry masters who could read the rock and direct the splitting of blocks. There were the stone dressers, skilled craft workers who shaped rough stone into precise geometric forms. There were the route planners who surveyed the land for the easiest path, and the rope makers whose product had to be strong enough to move mountains. Each role required deep, specialized knowledge passed down through generations, creating a living library of practical skills. This level of organization implies a clear hierarchy, a chain of command that could translate a single visionary design into actionable tasks for thousands. How did they maintain the morale and motivation of a workforce engaged in back-breaking labor for a project they might never see completed? The answer lies in a powerful, shared belief system and a culture of collective purpose. The construction site was likely more than a workplace. It was a sacred space, a focal point for community identity and spiritual life. The very act of building may have been imbued with ritual significance, turning labor into a form of devotion or a civic duty. Seasonal work patterns aligned with agricultural cycles would have allowed people to contribute during periods of less intensive farming, making the monumental task a part of the natural rhythm of life rather than a constant burden. The provisioning of this workforce points to a sophisticated economic system operating in the background. Supplying daily food for thousands required vast agricultural surpluses, managed distribution networks, and likely a form of tribute or taxation. The creation of standardized tools found in large caches at some sites suggests centralized production and allocation, a prehistoric supply chain ensuring that every worker had what they needed. This colossal coordination, spanning generations, stands as a silent testament to the human capacity for collaboration. The true miracle may not be the moving of the stones, but the moving of the people, the ability to unite an entire society around a single, enduring goal that would outlive them all. The sky was not just a spectacle, it was a blueprint. Ancient astronomers spent generations watching the slow dance of the heavens, meticulously tracking the sun's shifting path, the moon's complex cycle, and the steady march of the stars. This was not a passive hobby, it was a rigorous science of pattern recognition, a long-term project of data collection that transformed celestial motion into a reliable calendar etched into stone. At Mycenae, a magnificent tomb in Orkney, the entrance passage is aligned so perfectly that the setting sun of the winter solstice illuminates the inner chamber, a feat that required predicting the sun's most southerly position on the horizon years in advance. How could they possibly record these subtle annual shifts without any written language? Their tools were both monumental and mundane, simple wooden stakes driven into the ground could become a permanent observatory. By marking the position of a star's rise or a solstice sunset against a distant notch in the hills year after year, they built up a visual map of the sky's behavior. Some researchers suggest they used horizons as a giant natural protractor, using the dips and peaks of the landscape as fixed reference points to measure the sun's gradual slide. This celestial knowledge was then translated directly into architecture, serving a profound dual purpose. On a practical level, these alignments created a communal calendar, signaling the precise times for planting and harvest, governing the very rhythm of survival. Ceremonially, they connected the human world to the cosmic order, turning a stone circle into a place where the community could witness the universe reaffirming its cycles. The famous Stonehenge heel stone, for instance, marks the spot where the midsummer sun rises, an event that would have drawn people from across the land to witness the rebirth of the sun's power. This integration required more than just observation. It demanded a form of early mathematics. To transfer an alignment from an observing station to a distant construction site, they needed geometry. By using long ropes to create massive triangles on the landscape, they could project lines across miles with stunning accuracy. The development of simple gnomons, the earliest sundials, allowed them to track the sun's altitude and even establish true north. This was celestial engineering in its purest form, a holistic approach that saw no separation between the laws governing the stars and the principles of building on Earth. The very act of raising a stone to catch a specific ray of light was a declaration that humanity was part of a vast, intelligible cosmos. These modern experiments in ancient engineering are far more than academic exercises. They are physical conversations with the past where the proof lies not in a document, but in the successful lift of a multi-ton stone using nothing but timber, rope, and human ingenuity. When teams of archaeologists and volunteers dedicate themselves to using only replica tools, they often uncover efficiencies that theory alone could never predict. One of the most profound revelations is how quickly a skilled team can learn to move the seemingly immovable. In a famous experiment in France, volunteers using a sledge and rollers transported a 35-ton stone block over a considerable distance in just a few hours. This was not a feat of brute strength, but of coordinated rhythm and technique. The learning curve was steep and telling. The first attempts were slow and clumsy, but with each repetition, the team developed a fluid, almost musical synchronization. This observable progression strongly suggests that ancient construction relied on a core group of highly trained specialists, not vast armies of untrained laborers. These specialists would have honed their skills through a lifetime of apprenticeship, passing down nuanced knowledge that turned a chaotic tug of war into a graceful, efficient operation. This changes our entire perception of the required workforce. Rather than needing thousands, a project might have been managed by a few hundred seasoned professionals directing the work. This, in turn, compresses the imagined construction timelines for many monuments, suggesting they could have been completed within a single generation's determined effort. Perhaps the most surprising discovery from these reconstructions is the sheer intelligence embedded in the simplest tools. A team attempting to raise a massive standing stone might struggle for days with modern assumptions, only to have a breakthrough by employing a method described in local folklore or hinted at in an ancient carving. The use of a timber crib, a box-like frame that can be packed with stones to incrementally lift a load, has proven incredibly effective. Another experiment demonstrated how a stone can be rocked and walked into a prepared hole using levers, a method that feels less like construction and more like a carefully choreographed dance. These are not primitive methods, they are brilliantly adapted solutions that leverage physics in the most direct way possible. What emerges from the dust and strain of these experiments is a deep respect for the cumulative wisdom of the craft. Every successful lift validates 1,000 past failures and refinements. It reveals a forgotten truth that the true blueprint for these monuments was not on parchment, but in the practiced hands and shared rhythm of the people who built to last. The material that defined an era was surprisingly soft against the unyielding granite it was meant to shape. Bronze, for all its revolutionary allure, was a material better suited for carving wood or engraving symbols than for wrestling with multi-ton blocks. A bronze chisel struck against dense sarsen stone would bend and dull in minutes, becoming little more than a decorative tool in the face of such a monumental task. This presents a fascinating puzzle. How did an age named for its metal produce stonework of such precision that it seems to defy the very limitations of its primary tools? The answer lies not in a single miracle substance, but in a clever hierarchy of materials, where each was assigned the job it was best suited to perform. Bronze likely served as the master's finishing tool, used for the final delicate dressing, for incising those intricate spirals and patterns we still marvel at today. For the heavy work, the real engineering, builders relied on a far more ancient and resilient technology, the power of stone itself. They understood that to shape a mountain, you need a piece of the mountain. Harder stones like dolerite or quartzite were carefully fashioned into heavy mauls and pounders. Teams of workers would use these stone hammers in a relentless, rhythmic percussion, pulverizing the surface of a granite block grain by grain. It was a slow, deliberate process, a conversation of patience between one rock and another. This was not crude bashing, it was a controlled method of reduction. By striking along a desired line, they could create a shallow groove and then systematically fracture away the unwanted material. For the finest work, for achieving those perfectly smooth, almost polished surfaces, they turned to abrasives. Sand, a substance as simple as it is effective, was poured onto the stone surface. Then, using a flat piece of wood or sandstone as a sander, workers would grind the surface back and forth. The individual grains of sand, harder than the surrounding rock, acted as countless microscopic chisels, slowly scouring the stone to a flawless finish. This method could achieve a level of precision that a metal tool could never match, creating the breathtakingly tight joints that lock these monuments together. The true genius was in knowing which tool to use for which task. A stone maul for the rough shaping, a wooden wedge soaked in water to split the stone along its natural grain, and a sand abrasive for the final, perfect surface. This was appropriate technology in its purest form, an engineering philosophy that prioritizes the most effective solution over the most technologically advanced one. It reveals a society that looked at the world around them and saw a fully stocked workshop, where every material, from the hardest rock to the softest sand, held a potential waiting to be unlocked by human ingenuity. A corbelled arch is a conversation with gravity, a negotiation in stone where each layer leans inward, promising to hold the one above. Builders discovered they could create soaring, domed chambers without a single keystone by following a simple, brilliant rule. Each course of stone was laid so that it projected slightly beyond the one below, steadily narrowing the gap overhead until the final capstone could seal the chamber. The genius of this method is its distribution of force. The immense weight of the stones is not a threat to the structure, it is its very source of strength. The downward force is transformed, channeled into a powerful outward and downward thrust that compresses the entire assembly, locking every stone more firmly in place. This is the principle of compression in its purest form, a self-reinforcing system where the load becomes the glue. The treasury of Atreus in Greece stands as the ultimate testament to this engineering. Its massive, beehive-shaped chamber rises to a breathtaking height, every stone meticulously positioned to ensure that for over 3,000 years, not a single one has shifted. Walking into that space is to stand inside a perfected idea, a hollowed-out mountain of human calculation. How did they achieve such perfection without the safety net of mathematical formulas? The answer lies in a long history of observation and incremental improvement. The first attempts were likely small, experimental structures, perhaps storage pits or ceremonial spaces where a collapsed roof was a manageable lesson. With each success and each failure, the rules became clearer. They learned that the angle of the inward lean was critical, too steep, and the structure would become unstable, too shallow, and it would never close. They discovered that the thickness of the walls had to be proportional to the diameter of the chamber, providing enough mass to absorb and redirect the tremendous outward thrust. This was not abstract physics, it was a tactile science, learned through the feel of a settling stone and the sound of a well-placed block. The trial and error was a sacred process, a cumulative dialogue between the builders and the materials, where every generation inherited the refined wisdom of the last. The resulting vaults were more than just roofs, they were shelters for eternity, designed to stand as long as the earth itself, a perfect marriage of ambition and stone-cold logic. The silent rivers and coastal waters of the ancient world were not barriers but highways. Some of the most profound engineering puzzles involve moving stones across vast liquid distances, a task that required a completely different kind of thinking. While land transport relied on rollers and sledges, moving a megalith across a river or sea channel demanded an understanding of buoyancy and balance that feels remarkably advanced. Evidence from across Europe suggests that Bronze Age engineers became masters of maritime logistics, constructing sophisticated floating platforms capable of bearing weights that would sink a conventional wooden boat. The most famous example is the journey of the Stonehenge bluestones, transported over 150 miles from the mountains of Wales. This incredible trek almost certainly involved a multi-stage journey, where the stones were hauled overland to a waterway, loaded onto rafts, and then floated along the Welsh coast and up rivers before the final land journey to Salisbury Plain. How could such simple technology achieve such a monumental task? Recent experimental archaeology has provided stunning answers. Teams have built rafts using only materials available at the time, such as timber and animal hide, and have successfully floated multi-ton stones. The secret lies not in a single giant raft, but in the principle of distributed buoyancy. By lashing several large, hollowed-out logs together to create a stable, barge-like platform, they could create enough upward force to keep the stone afloat. The challenge of loading was met with equal ingenuity. Builders likely constructed simple stone piers or earthen ramps that extended into the water. A stone could be dragged onto a waiting raft at low tide, and as the tide rose, the raft would lift, freeing itself from the ramp and becoming fully buoyant. This elegant solution harnessed the natural, predictable power of the moon to do the heavy lifting. Unloading at the destination would have used the same tidal process in reverse. This required not just engineering skill, but precise astronomical and tidal knowledge, planning the entire journey around the lunar cycle. The logistics of guiding these cumbersome vessels also point to a deep understanding of hydrodynamics. Steering such a heavy, slow-moving raft would have been nearly impossible with paddles alone. It is more likely they used a combination of towing from smaller boats and strategically placed anchor stones. By dropping a heavy anchor from the stern or the bow, they could pivot the entire raft using the current itself to help steer. What evidence supports these watery journeys? While the organic materials of the rafts have long since decayed, archaeologists have found suggestive clues. At the quarries for the Stonehenge bluestones, for instance, the specific route to the coast is one that naturally avoids the steepest gradients, pointing to a pre-planned logistics chain designed for water transport. In other regions, carvings and later historical accounts from cultures like the Egyptians vividly depict the transportation of massive statues on giant reed boats, confirming that the principle was widely understood. This maritime dimension reveals a society that saw the entire landscape as an integrated system, where rivers, seas, and land were all connected parts of a single transportation network. It showcases a technological capability that was not just about moving stone, but about mastering the elements themselves. Their structures still stand because they learned to speak the silent language of force and balance. Bronze Age builders developed a deep, intuitive grasp of structural physics, a mathematical understanding of how weight flows through stone and how to guide it safely into the earth. This was not a science of complex equations, but of empirical observation, a knowledge built by watching how stones settled, how walls leaned, and where stress revealed itself as a hairline crack. They understood that a stone block under compression becomes stronger, its crystalline structure locking tighter under the load, while the same stone pulled in tension is vulnerable to fracturing. This fundamental insight informed every decision, from the placement of a single lintel to the overall form of a massive tomb. The great trilithons at Stonehenge are perfect examples of this principle in action. Each massive horizontal lintel is not merely resting on its uprights. The connecting surfaces were often subtly shaped with mortise and tenon joints, locking the stones together. This design ensures that the immense weight of the lintel transfers straight down through the uprights as pure compressive force, a direct and stable path into the ground. How did they identify these critical tension and compression points without modern stress analysis? Their laboratory was time itself, and their data was written in the failures and successes of every previous generation's work. They observed which architectural forms remained standing after a storm or a minor earth tremor, and which ones crumbled. A collapsed corbelled roof taught a vivid lesson about the limits of inward lean, while a wall that had stood for a century demonstrated the perfect balance of mass and support. This process of continuous refinement, of learning from both triumph and disaster, slowly built a reliable body of knowledge about structural behavior. This practical mathematics also expressed itself through proportional design. Builders discovered that certain ratios between the height of a wall and its thickness, or the span of a roof and the weight of its supporting stones, consistently produced stable structures. These were not arbitrary aesthetic choices, but codified solutions to the universal problem of load management. A passage tomb with a diameter of 10 units might require walls with a thickness of 2 units, a ratio that experience had proven would effectively channel the outward thrust of the vaulted roof. This allowed for the confident scaling of designs, ensuring that a small shrine and a grand temple both adhered to the same inherent laws of stability. The transmission of this complex understanding was a sacred trust, passed from master craft worker to apprentice on the construction site itself. Through gesture, demonstration, and the shared experience of raising stone together, each generation learned to feel the balance of a structure, to sense the flow of forces through the materials they handled every day. This was a living mathematics written not on parchment, but in the perfect, enduring alignment of one stone upon another. Across the vast expanse of mountains and seas, a silent conversation was taking place. The proof of this dialogue is etched in stone, found in the uncanny similarities between monuments separated by hundreds of miles. A stone circle in Britain shares a fundamental design principle with a tomb in the Mediterranean, not by coincidence, but because the blueprint for its construction traveled. This was a continent-wide web of knowledge, a sophisticated system of cultural transmission that moved ideas as reliably as any trade good. The vehicles for this exchange were the ancient routes that carried amber, tin, and luxury items. Along these paths, something far more valuable than material wealth was exchanged, the intangible currency of engineering insight. A master builder traveling with a merchant caravan would have been a living library, carrying a measuring rod and a mind full of geometric secrets. He could observe a problem solved in one river valley and bring that solution to a distant coast where local builders would adapt it to their own materials and beliefs. This was not a simple act of copying, but a dynamic process of creative adaptation. How could such complex, hands-on knowledge be shared without a single written manual? The answer lies in the world's first professional networks, the specialized builder guilds that preserved this technical wisdom. Within these groups, knowledge was a sacred trust, passed meticulously from experienced craft worker to apprentice through years of direct practical training. An apprentice would not just be told how to shape a stone, he would spend years feeling the correct angle of the hammer strike, learning to listen to the sound the rock made as it was worked, understanding the subtle differences between granite and limestone through his own hands. This was a living, breathing education system where failure was an immediate and unforgettable lesson, and success was a technique refined over a lifetime. The consistency of the prehistoric yardstick found across Europe is the ultimate evidence of this system. It means that a unit of measure in one land was identical to that 1,000 miles away, a feat that required the creation and maintenance of physical master standards. These standardized rods, likely crafted from durable wood or stone and kept by elite surveyors, ensured that a design for a stable arch or a perfectly aligned passage could be reliably replicated anywhere. This cultural engineering created a powerful feedback loop. A successful innovation in one region could be tested and refined in another, with the best solutions surviving and spreading. It meant that the collective intelligence of an entire continent was being brought to bear on the fundamental challenges of construction, turning isolated flashes of genius into a sustained collective legacy that would endure for millennia. The true monument was not any single circle of stones, but this invisible, resilient network of shared human thought. Every landscape presented its own unique set of rules, and Bronze Age engineers proved to be masterful students of their environment. They did not impose a single, rigid blueprint onto the world. Instead, their methods evolved in a direct conversation with the local geology, climate, and topography. In the rugged highlands of Scotland, where granite outcrops dominated the skyline, builders learned to work with the natural fracturing of the bedrock. They would seek out stones already shaped by millennia of ice and weather, minimizing the need for extensive shaping and leveraging the inherent strength of these time-hardened monoliths. The resulting blocks, those mysterious dry stone towers, seem to grow directly from the landscape, their forms a direct response to the available stone and the relentless wind. Contrast this with the river valleys of Wessex, where the great sarsen stones littered the chalk downs. Here, the challenge was not finding material, but moving it across a softer, more rolling terrain. This led to the refinement of sledge and roller technology, with routes carefully planned to avoid the steepest gradients and to utilize the natural slipways of frozen winter ground. The very tools they used were shaped by their surroundings. In regions rich with flint, they crafted razor-sharp chisels and pounders. In areas where hard stone was scarce, they perfected the use of fire setting, heating the rock surface and then rapidly cooling it with water to create spalls and fractures that could be worked. This was not a one-size-fits-all approach, it was a deeply localized science. How did they develop such specific, adapted techniques? It was a process of continuous, on-the-ground experimentation. A method that worked perfectly in the limestone hills of Malta would be useless in the boggy soils of Ireland. There, builders facing unstable, waterlogged ground displayed incredible foresight. They constructed intricate foundations of brushwood and timber, creating a stable, crisscrossed mattress that distributed the weight of massive stones and prevented them from slowly disappearing into the earth. This principle of working with nature rather than conquering it is perhaps their most enduring engineering legacy. They looked at a swamp and saw a foundation waiting to be built. They studied a mountain and saw a quarry already prepared. Their greatest breakthrough was understanding that the environment was not an obstacle to overcome, but the most important partner in their ambitious projects. The stone was more than a building block, it was a vessel for meaning. When a community invested generations in raising a monument, every engineering choice was infused with a deeper significance that went far beyond structural necessity. The specific type of granite chosen for a central pillar might have been selected not only for its strength, but because it originated from a sacred mountain, believed to hold the power of ancestors. The act of transporting that stone from its distant source could have been a ceremonial pilgrimage, a physical journey that mirrored a spiritual one, with the difficult path itself becoming a rite of passage. The engineering was never separate from the belief system, it was its physical expression. This is why the alignment of a passage tomb to the winter solstice sunrise was engineered with such breathtaking precision. The goal was not just to mark a calendar date, but to create a moment of celestial drama, a guaranteed miracle where the sun would reclaim the dark world right on schedule, reinforcing the community's faith in the cosmic order. The architecture was designed to frame this event, to make the invisible forces of the universe visible and tangible for everyone present. How did this symbolic drive influence technical development? It often pushed engineering into new territories. The desire to create resonant chambers for ritual chanting likely led to experiments with chamber shape and stone composition, accidentally advancing the understanding of acoustics. The need to orient a temple precisely to a specific star might have demanded more accurate surveying tools and geometric principles, refining the very science of measurement. What seems like an impractical extra step to a modern engineer, such as transporting bluestones over 150 miles to Stonehenge, becomes perfectly logical when you understand that those stones were believed to possess unique healing properties. The immense logistical challenge was not an obstacle, it was part of the point, a testament to the value of the spiritual cargo. This fusion of the sacred and the practical created a powerful feedback loop. A successful ritual, amplified by perfect acoustics and celestial alignment, reinforced the community's belief in their leaders and their gods. This social cohesion, in turn, provided the sustained motivation and organized labor needed to undertake even more ambitious engineering projects. The monument became a self-justifying cycle of faith and capability, where the act of building strengthened the belief that made the building possible. The true engineering marvel, then, was not just the standing stone, but the seamless fusion of physics and faith, of rope and ritual, into a single, enduring testament to a culture's identity. Those ancient principles of stone and balance never truly vanished from the world. They simply found new homes, their logic echoing through the grand constructions of Greece and Rome. The classical world, for all its marble glory, stood firmly upon a Bronze Age foundation. The Greeks perfected the use of massive, unmortared stone blocks in their Cyclopean walls, a direct inheritance from Mycenaean builders who understood how interlocking shapes could create unshakable stability. The Romans, masters of empire, took this inherited knowledge and scaled it to breathtaking new heights. While they famously developed concrete, their most enduring structures still relied on the ancient wisdom of foundation engineering. Before laying a single road or raising an aqueduct, Roman engineers would excavate down to stable ground and build up layers of crushed stone and mortar, creating a platform that could bear immense weight for centuries, a direct echo of the practices used to support Bronze Age mounds 1,000 years earlier. Even the precise proportional design of the Greek temple, with its harmonious columns and pediments, can be traced back to the same geometric ratios that guided the layout of prehistoric stone circles. This was not a rediscovery, but a continuous thread of applied knowledge passed down through generations of craft workers. The great Gothic cathedrals of the medieval period, reaching impossibly toward the heavens, also owe a debt to this deep past. Their soaring vaults are the spiritual descendants of the Corbeled arch, a Bronze Age innovation that taught builders how to channel weight downward and outward into massive supporting piers. The master masons who constructed charters or Notre Dame were studying the same physics of compression and thrust that Bronze Age engineers had mastered in their beehive tombs, just expressing it on a more colossal and luminous scale. Why did these specific techniques persist when so much other knowledge was lost to time? The structures themselves were the answer. A Roman aqueduct still carrying water or a Mycenaean wall still standing after an earthquake were not just ruins, they were active, functioning proof. They served as living textbooks for later engineers, providing undeniable evidence of which principles worked. The endurance of a dry stone wall across millennia was a lesson no theoretical manual could ever match. This unbroken lineage reveals a profound truth, that the most fundamental engineering solutions are timeless, transcending the rise and fall of empires to become a permanent part of humanity's architectural language. The principles that built monuments for the ages are now finding new life in our modern world. Architects and engineers facing today's climate challenges are looking back to Bronze Age ingenuity for sustainable solutions. These ancient builders achieved incredible durability without high energy costs or complex machinery, creating a blueprint for a more resilient future. The passive solar design of a Neolithic tomb, perfectly aligned to capture winter sun, is a direct ancestor of modern green building standards. Contemporary architects now study these orientations to reduce heating and cooling demands in new structures, using the sun as a free energy source just as ancient builders did. The massive stone walls that acted as natural thermal batteries are inspiring modern designs that incorporate dense materials to stabilize indoor temperatures, drastically cutting down on the need for mechanical systems. This is not nostalgia, it is a practical rediscovery of physics that has worked for thousands of years. The aesthetic and environmental benefits of dry stone construction are also being re-evaluated. Modern builders are creating stunning, mortar-free walls for gardens and public spaces, recognizing that these structures are not only beautiful but perfectly permeable, managing rainwater runoff far better than solid concrete. They are durable, require no manufactured materials, and can be dismantled and reused without creating waste, embodying the ultimate in circular design. The incredible resource efficiency of Bronze Age methods offers a powerful critique of our own disposable building culture. They used locally sourced materials, minimizing transportation energy, and designed for permanence rather than planned obsolescence. How can these principles inform our approach today? The answer lies in shifting our mindset from conquering nature to collaborating with it. By choosing materials for their long-term performance and designing structures that work with natural forces like gravity, sunlight, and wind, we can create buildings that are not only sustainable but are designed to become the ancient monuments of tomorrow. The greatest lesson these stone sentinels teach us is that true sustainability is measured in millennia, not just in decades. Some stones fit together so perfectly that the seam is nearly invisible, a level of precision that still defies easy explanation. Even with our advanced tools and centuries of study, key aspects of how these monuments were built remain shrouded in mystery. The methods used to transport the largest stones, like the 200-ton monoliths at Baalbek, are a subject of intense debate, with theories ranging from colossal rolling mechanisms to complex systems of levers that we have yet to fully replicate. The social organization required to coordinate thousands of workers for generations is another profound puzzle, leaving little trace of the administrative systems that must have managed such colossal efforts. Just when we think we have the answers, new technologies reveal another layer of complexity. Ground-penetrating radar has uncovered vast, hidden networks of stones and post holes beneath the visible sites, suggesting that what we see today is merely the final phase of a much larger, more intricate architectural plan. Three-dimensional laser scanning has detected subtle marks on stone surfaces that hint at sophisticated shaping techniques we do not entirely understand. These are not just academic curiosities. Each new finding forces us to reconsider the very timeline of human innovation. A recent discovery at a site in Turkey, for instance, revealed carved stone pillars with intricate reliefs that predate what was considered possible for that period by several centuries. This single finding challenges the linear progression of technological development, suggesting that advanced engineering knowledge appeared, was lost, and then reappeared in a cycle we are only beginning to map. What does this mean for our understanding of the past? It means the story is not yet written in stone. Every time a new scan reveals a hidden chamber or a fresh excavation uncovers an unexpected tool, we are reminded that the Bronze Age builders still have secrets to share. The true scale of their achievement may be even greater than we currently comprehend. These silent stone sentinels reveal a world of intelligence we are only beginning to decode. Our journey through the hidden engineering of the Bronze Age uncovers a reality far from primitive, a time of sophisticated knowledge and remarkable innovation that touched every aspect of life. It was not a single secret that allowed them to build for eternity, but a comprehensive system of interconnected principles, from the deep material science of selecting the perfect stone to the complex social organization required to marshal a workforce for generations. These builders developed a complete philosophy of creation. They saw no separation between the practical and the sacred, the earthly and the cosmic. Their architectural achievements were the physical result of this holistic vision, a perfect alignment of human ingenuity with the fundamental laws of the natural world. The enduring legacy of their work continues to inspire and quietly challenge our modern understanding of human capability. As we reflect on these ancient breakthroughs, we recognize timeless lessons about the power of collaboration, the necessity of adapting to our environment, and the boundless potential of creatively applied knowledge. The stones themselves, still standing after thousands of years, are the ultimate testament to what we can accomplish when a clear vision meets unwavering determination. We would love to hear which of these ancient marvels inspires you most, so please share your thoughts in the comments below. And if you are curious to continue exploring history's greatest mysteries with us, be sure to subscribe for our next journey into the past.